I want you to start with a number, because physics begins with measurement, not imagination. And the number I want you to hold in your mind is 100,000. Not kilometers, not miles, but light years, which is the approximate diameter of the Milky Way. And already your intuition begins to fail, because a light year is not just a distance. It is the distance light travels in a year, about 46 trillion kilometers. So when I say 100,000 light years, I am telling you that even the fastest thing allowed by the universe itself, light, would need 100,000 years to cross from one side of our galaxy to the other. And that single fact should immediately change the way you look at the night sky. Because the stars above you stop being reachable destinations and start becoming timestamps, frozen across enormous stretches of time. You and I have been quietly conditioned to think otherwise, because every piece of science fiction you've ever encountered suggests that distance is just a technical inconvenience. That if we invent warp drives, hyperspace corridors, or engines powerful enough, the Milky Way becomes a navigable territory. But this assumption sneaks in a dangerous idea, the belief that technology can eventually overcome any barrier. And that belief works perfectly well on Earth, where oceans once seemed uncrossable until ships appeared, where continents felt isolated until aircraft connected them. Yet the barrier imposed by the galaxy is not made of water or atmosphere. It is built into the structure of space-time itself. And unlike mountains or oceans, space-time does not yield to engineering, because it is the stage upon which engineering exists. To see how misleading our intuition is, imagine you are looking at the Milky Way not as a glowing band in the sky, but as a physical structure. A flattened, rotating disk filled with hundreds of billions of stars, vast clouds of gas, dark matter halos, and enormous empty regions where nothing exists for trillions of kilometers. And somewhere in one of the spiral arms sits our sun, an ordinary star orbiting the galactic center at nearly 800,000 kilometers per hour, which sounds unbelievably fast until you realize that at that speed, it still takes about 230 million years to complete a single orbit, meaning our entire solar system is already trapped in a slow cosmic carousel, moving through space on timescales so large that human history does not even register as a fraction of a turn. Now here is where the illusion begins to crack, because when you look at stars, your brain treats them as fixed points, as if the galaxy were a static map. But in reality, every star is moving, the entire disk is rotating, gravitational interactions constantly reshape trajectories, and the distances between stars are so immense that even light takes years, centuries, or tens of thousands of years to travel between them, which means the galaxy is not a still landscape, but a dynamic system where both space and time stretch to scales that undermine any simple notion of travel. And when you begin to think in those terms, crossing the Milky Way stops being a journey and starts looking like an attempt to outrun geological epochs. The deeper problem, and this is the part that changes everything, is that the speed of light is not just fast. It is the maximum speed allowed by the universe. And this is not a technological limit, but a fundamental one arising from the geometry of space-time described by Einstein, which means any object with mass requires increasingly infinite energy as it approaches that speed. So the dream that we might simply build a faster ship runs into a wall that is not made of matter but mathematics. And mathematics does not bend under pressure. It simply tells you what is allowed and what is forbidden. And in this case, it tells you that even in the most optimistic scenario imaginable, the galaxy cannot be crossed quickly enough for human timescales to remain meaningful. So when you look up tonight and see that soft band of light stretching across the sky, what you are really seeing is not a road, not a frontier, not a destination, but a structure so vast that the very rules of physics transform distance into isolation, and the Milky Way, instead of being an open ocean inviting exploration, becomes something far more unsettling, a cosmic enclosure where every civilization, no matter how advanced, finds itself confined by the same silent boundaries written into the fabric of reality. The real problem with the Milky Way is not that it is large, but that it is large in a way the human brain was never built to handle. You and I can understand a road, a city, a country, even a planet if we reduce it to maps, flights, and travel time. But once astronomers begin talking about tens of thousands of light years, the numbers stop producing images and become empty labels. And that is dangerous, because the moment a number becomes only a label, you lose your grip on the physical reality behind it. So instead of beginning with equations or astronomical tables, it is better to build a scale model, because scale is the only bridge between cosmic truth and human intuition. Take the entire solar system, not just Earth's orbit, not just the giant planets, but everything from the sun out to Neptune, and compress it until it fits into the size of a $1 coin resting in your hand. On that scale, the sun is no longer a giant star, but a tiny center point. The planets are almost nothing. And Earth, the whole stage of human history, is so small that it barely deserves the name of an object. Now the question becomes interesting, because once you have that coin in your hand, you could ask where the next coin would be. If the solar system is that small, then the nearest star system, Proxima Centauri, does not sit on the table beside it, and it does not even sit across the room. It would be roughly 100 meters away, about the length of a soccer field, which means that even after crushing the solar system down to the size of a coin, the universe still insists on separating stars with huge volumes of nothing. That is the first correction your intuition has to accept. The galaxy is not densely packed with destinations waiting for travelers, but mostly empty space. With rare islands of matter scattered across it, science fiction trains you to imagine traffic between stars, but the true picture is closer to a desert, so vast that even the oases are almost irrelevant compared with the emptiness between them. Keep that same scale and push the model outward. If one solar system is a coin, and the nearest star is another coin, placed a soccer field away, then the Milky Way is no longer something you can draw on a classroom wall or picture as a bright stripe in the sky. It expands to the size of a continent, not a city, not a country, but something comparable to North America in extent, filled with hundreds of billions of stars that still remain, on average, shockingly isolated from one another. At that point, the meaning of our position changes. We are not residents of some bustling cosmic metropolis. We are inhabitants of one tiny metallic speck lying somewhere in the grooves of a continent-scale structure. And most of that structure is darkness, distance, and silence. What makes this more unsettling is that our daily language constantly betrays us. We say the nearest star as if it were nearby, in any practical sense. But on the scale that preserves the true proportions of the universe, nearest still means separated by a field of emptiness so large that human travel loses all familiar meaning. We say our galaxy as if ownership implied accessibility, but nothing in the structure of the Milky Way suggests accessibility. The words are small, comfortable, and human. The reality is not, once you translate the galaxy into a scale the mind can actually examine, you begin to understand that the challenge is not merely one of better machines, It is that the basic layout of our environment is already hostile to movement on civilizational timescales, and that is the point of the exercise, not to admire how big the galaxy is in some abstract poetic way, but to correct a false instinct. The Milky Way is not difficult to cross only because we are technologically young. It is difficult because even after you shrink it to a form the mind can manage, the proportions remain extreme. The stars do not form a convenient network. They form a sparse structure spread across a scale that reduces human experience to something almost microscopic. Once that picture settles properly in your head, the galaxy stops looking like a destination and starts looking like a problem of distance in its purest form. To understand how far we really are from crossing the Milky Way, we should stop talking about hypothetical future engines and instead use something real, something that already exists, something built by human hands and pushed to the edge of engineering limits. The fastest object humanity has ever created is NASA's Parker Solar Probe, a spacecraft designed not to travel between stars but to dive repeatedly toward the sun, using gravity itself as a slingshot, falling deeper into the sun's well and stealing a little more speed each time, until it reaches velocities that are almost absurd by everyday standards, roughly 700,000 kilometers per hour. On Earth, that speed feels almost unreal. At that velocity, you could circle the planet in minutes, cross continents in moments, and leave any aircraft ever built far behind. It represents the peak of modern propulsion combined with gravitational mechanics, and it is not a theoretical number but a measured one, achieved in the real universe under real constraints. Now take that speed and imagine turning it outward, away from the sun, away from planets, away from everything familiar, pointing a spacecraft toward the opposite side of the Milky Way. Nothing exotic, no warp drive, no speculative physics, just the fastest velocity humanity has ever achieved. The galaxy is about 100,000 light years across, which corresponds to a distance so large that even writing it in kilometers becomes meaningless. But when you combine that scale with the speed of the Parker Solar Probe, the travel time emerges from simple arithmetic, and the result is staggering. The journey would take roughly 7 billion years. That number does not feel real at first, because billions of years are outside human experience. So it helps to compare it with something familiar. And the most familiar clock we have is Earth itself. Our planet is about 5 billion years old, which means crossing the Milky Way at the fastest speed humanity has ever achieved would take more than a third of Earth's entire lifetime. If you rewind Earth's history by 7 billion years, you do not find dinosaurs, forests, or complex animals. You find a world dominated by single-celled organisms drifting in ancient oceans under a very different atmosphere, continents arranged in unfamiliar shapes, no plants on land, no animals walking across continents, nothing resembling the biosphere. You know, today, that is how far back in time you must go to match the duration of this journey. In other words, if microscopic life on early Earth had somehow launched a spacecraft at our current maximum speed, that ship would only now be reaching the opposite side of the galaxy. The entire rise of complex life, the Cambrian explosion, the age of dinosaurs, the extinction events, the emergence of mammals, the evolution of humans, agriculture, cities, science, and spaceflight itself would all have unfolded while that single spacecraft drifted across interstellar darkness. This comparison exposes something uncomfortable about technological optimism. We tend to assume that once we achieve space travel, scaling it up to interstellar journeys is just a matter of iteration. Faster engines, larger fuel reserves, improved materials, but the gap between planetary travel and galactic travel is not linear. It is not like upgrading from ships to airplanes. It is closer to comparing the lifespan of a human to the age of a continent, even at speeds that feel extreme to us. The galaxy remains effectively immovable on human timescales. The spacecraft does not race across it. It crawls. The distinction matters because when travel times stretch into billions of years, the journey stops being an expedition and becomes something closer to geological drift, a slow migration through space that outlasts species, climates, and even planetary ecosystem. There is also another subtle point hidden in this calculation. The Parker Solar Probe reaches its enormous speed by falling toward the sun and using gravitational assists, a method that works brilliantly inside a solar system but becomes much harder to replicate in interstellar space where stars are separated by vast emptiness. In other words, even this record speed is not something you can simply maintain across the galaxy. It represents a peak achieved under very specific conditions, not a cruising velocity that a ship could hold for billions of years. So the 7 billion year estimate is already generous, already optimistic, already assuming we can sustain what is essentially a brief sprint forever. When numbers are this large, the meaning of speed changes. 700,000 kilometers per hour sounds like motion, but against galactic distances it becomes almost indistinguishable from stillness. The fastest machine we have ever built, pushed to its absolute limit, does not open the galaxy to us. It barely shifts our position within it, like an insect moving across a continent, hovering ground in its own frame of reference, while the landscape remains effectively unchanged. Suppose, for a moment, that every technological limitation disappears, that propulsion, energy generation, shielding, and navigation all reach perfection, and that humanity somehow manages to build a spacecraft capable of traveling at the ultimate speed allowed by nature, the speed of light itself, about 300,000 kilometers per second. This is not merely fast, it is the maximum rate at which cause and effect can propagate through space-time, the limit encoded in the structure of relativity, meaning nothing carrying mass can actually reach it. But imagine we could approach it closely enough that the distinction no longer matters. For a rough estimate, if such a ship departed from Earth today and aimed straight across the Milky Way, the travel time would not be days or centuries or even millennia. It would take about 100,000 years to reach the opposite side. At first glance, 100,000 years may sound manageable compared with the billion-year timescale of slower technologies, but this is where human intuition fails again, because our sense of long time is shaped by history, and human civilization itself is astonishingly young. Agriculture began roughly 10,000 years ago. Written language, cities, empire, philosophy, science, industry, and modern technology all fit inside that narrow window. The pyramids, the Roman Empire, the rise and fall of kingdoms, the Industrial Revolution, the World Wars, and spaceflight happened in less than a tenth of the time required to cross the galaxy at light speed. Multiply everything humanity remembers by 10, and you begin to see the scale. A crew leaving Earth today would travel for a duration 10 times longer than all recorded history combined. The consequences of that time span are not abstract. During 100,000 years, continents shift, climates oscillate, species evolve and vanish, and cultures transform beyond recognition. Languages drift until they become unintelligible. Myths replace facts, and entire civilizations rise and collapse without leaving more than fragments. If astronauts departed now, the Earth they knew would not exist when they arrived. Nations would dissolve, borders would change, and the political, technological, and social structures that launched the mission would belong to a remote past. Even if humanity survived, it would likely be culturally and biologically different, shaped by environmental pressures and technological developments impossible to predict across such an interval. The explorers would carry memories of a world that no longer has continuity with the one still orbiting the sun. Communication does not solve this problem. Because signals are bound by the same speed limit, a message sent from Earth would take tens of thousands of years to reach a ship halfway across the galaxy, and a reply would take equally long to return. Any conversation stretches into spans longer than the lifespan of civilizations. Orders, updates, or discoveries become meaningless because by the time information arrives, the context that made it relevant has vanished. The idea of coordinating a galactic society collapses under this delay. Authority cannot extend across epochs, and cooperation cannot survive when cause and response are separated by geological time. There is also a psychological dimension that follows naturally from these numbers. A crew traveling at light speed would not simply endure a long voyage. They would become detached from the temporal flow of their origin. Everything familiar culture, science, identity would be frozen at departure. While the rest of humanity continued to change, the travelers would effectively step outside shared history, moving through space while their species moved through time. When they finally arrived, they would not reconnect with the civilization that launched them, but with whatever had replaced it, assuming anything recognizable remained. The journey would not extend humanity outward so much as separate fragments of it, each drifting into different futures, with no practical way to reunite. Seen from this perspective, even the ultimate velocity permitted by physics does not make the galaxy accessible in any meaningful sense. It shortens the duration from billions of years to hundreds of thousands, but the underlying consequence remains. The travelers and those left behind cannot remain part of the same story. Movement across the Milky Way at light speed becomes less an act of exploration and more an irreversible divergence. Where distance in space quietly becomes distance in time, and the connection between departure and arrival dissolves long before the destination is reached. If traveling at the speed of light already fractures continuity between departure and arrival, then any realistic velocity makes the situation even more extreme, because once we accept that reaching such speeds is physically impossible for massive objects, the discussion shifts toward technologies that do not violate known physics, advanced fusion propulsion, antimatter engines, or other concepts grounded in speculative but plausible engineering. And these typically converge on a figure around 10% of the speed of light as an optimistic upper bound for sustained interstellar travel. At that velocity, the Milky Way does not shrink into something manageable. It still demands roughly 1 million years to cross from one side to the other. And the moment that number appears, the idea of a conventional crewed mission collapses, because no human lifetime can even approach that duration. The journey ceases to be a voyage and instead becomes an inheritance, something handed from one generation to the next without anyone alive ever seeing both the beginning and the end. This is where the concept of a generation ship emerges, not as a dramatic science fiction trope, but as a logical consequence of long travel times. The spacecraft would no longer be a vehicle carrying passengers. It would be a closed world carrying a population. Thousands of individuals might live inside a self-contained ecosystem designed to recycle air, water, and nutrients indefinitely with artificial gravity, controlled agriculture, and layered infrastructure functioning more like a drifting city than a machine. Children would be born inside metal corridors, grow up never seeing a natural sky, and inherit a mission whose origin lies centuries behind them, over thousands of years. This pattern repeats, births replacing deaths, memory turning into tradition, tradition turning into myth. The initial launch becomes a distant story preserved in archives that few read and fewer fully understand, while the daily reality of life aboard the ship becomes the only environment anyone has ever known. The biological implications of such isolation are unavoidable. Evolution does not require intention. It operates wherever variation and selection exist. And 1,000,000 years provides more than enough time for both. A population confined within a closed habitat would experience limited genetic mixing, persistent exposure to cosmic radiation, and environmental pressures different from those on Earth. Even small changes accumulated across thousands of generations begin to shift physiology. Bone density might adapt to artificial gravity levels slightly weaker than Earth's. Vision might adjust to artificial lighting. Metabolism could evolve around recycled diets. None of these changes would be dramatic at first, but over long intervals they compound, and the descendants of the original crew gradually diverge from their ancestors. Not through sudden mutation, but through continuous adaptation to an artificial world. Cultural evolution proceeds even faster. Languages drift within centuries. Accents shift. Vocabulary adapts to new conditions. And references to Earth lose clarity. After 10,000 years, the original languages would likely fragment into new dialects shaped entirely by shipboard life. After 100,000 years, historical memory weakens further, and the idea of oceans, continents, or open skies may survive only in symbolic form. Retold in educational rituals or simplified narratives, engineering decks might become associated with origin myths, agricultural zones with cycles of life, and the concept of Earth itself gradually transforms from a physical place into a foundational legend explaining why the ship exists. The mission continues, but its meaning changes, reinterpreted by generations who inherit the goal without sharing the perspective that defined it. By the time the ship approaches its destination, the beings aboard would not simply be humans who endured a long trip. They would be the result of prolonged isolation, shaped by both biological drift and cultural divergence. Their physiology, psychology, and social structures would reflect the environment of the vessel rather than the planet that launched it. The arrival would therefore not represent humanity expanding into a new region of the galaxy, but a lineage separated for 1,000,000 years, encountering a world that none of its members ever intended in the original sense. The voyage would have carried forward a seed, and what emerges at the end would be connected to us by ancestry, yet defined by a history that unfolded entirely in transit, shaped less by exploration than by adaptation to a closed, drifting habitat. Up to this point, the difficulty of crossing the Milky Way has come from distance and time. But there is another layer that makes the problem far more severe, and it begins with a quiet misconception about the night sky. When you look at the stars, your brain treats them as fixed points, like cities on a map, stable markers that you could aim toward and eventually reach. But the galaxy is not a static chart. It is a rotating, evolving system in constant motion. The Milky Way is a vast disk slowly turning in a gravitational ballet, with stars orbiting the galactic center at enormous speeds, including our own sun, which moves at nearly 800,000 kilometers per hour. That velocity sounds extreme, Yet it still takes more than 200 million years for the solar system to complete a single orbit. Every other star is moving as well, each following its own path shaped by gravity, interactions, and the distribution of mass across the galaxy. The result is not a calm ocean dotted with stationary islands, but a swarm of objects drifting through space, all in motion, all changing position continuously across cosmic timescales. This motion creates a subtle but profound problem for long-distance travel. When astronomers observe a star tens of thousands of light years away, they are not seeing that star as it exists. Now, they are seeing light that left the star tens of thousands of years ago. The image is already outdated by the time it reaches us. If a star lies 80,000 light years away, the light we detect today began its journey when early humans were still carving stone tools. In practical terms, we are always looking into the past. The further away the target, the older the information. This means that any mission aimed across the galaxy must begin by choosing a destination that is known only through ancient data. You are not plotting a course toward a current location, but toward a historical one, a snapshot frozen in time. Now combine this with the million-year travel durations of realistic generation ships during the time a spacecraft spends crossing the galaxy. The entire structure of the Milky Way continues to evolve. Stars drift along their orbits. Gravitational encounters alter trajectories, and regions that once appeared promising may shift thousands of light years relative to their previous positions. The target star you selected at launch will not remain where it appeared. By the time the ship approaches the predicted coordinates, the star could have moved significantly, requiring continuous recalculation and course correction based on progressively updated observations. Even that assumes the destination still exists. Stars are not permanent. Some fade gradually, while others end their lives violently as supernovae, releasing immense energy and potentially destroying surrounding planetary systems. A star that appeared stable in the original observations could have exploded hundreds of thousands of years earlier, with the light from that event still traveling toward the ship, not yet visible to warn its inhabitant. The navigation problem becomes less like steering toward a harbor and more like aiming at a moving object whose current position is unknown and whose future path depends on gravitational influences unfolding over vast intervals. The spacecraft must constantly update its trajectory using delayed information compensating for motion it cannot directly observe in real time. Even small uncertainties accumulate over such long durations, and predicting stellar positions over hundreds of thousands of years becomes increasingly unreliable. The travelers are effectively chasing a ghost, guided by models constructed from incomplete data, adjusting their path through a galaxy that refuses to remain still. This dynamic environment also affects the broader concept of galactic travel. It is not enough to choose a star and accelerate toward it. The entire route evolves. Interstellar clouds drift, gravitational fields shift, and neighboring stars pass closer or further away, subtly reshaping the gravitational landscape. Over 1 million years, these changes are not negligible. They redefine the geometry of the journey itself. The ship is not traversing a fixed distance, but moving through a continuously changing system where both the start and the destination belong to a past configuration that no longer exists in the same form. When distance, time, and motion combine, the challenge of crossing the Milky Way stops resembling navigation and starts resembling prediction on cosmic scales. The travelers must rely on models extending far beyond any tested horizon, adjusting their path through delayed observations, aware that their destination is not a stationary endpoint, but a moving participant in the galaxy's slow rotation. The voyage becomes an attempt to intercept something that is already elsewhere, guided by light that records what used to be, not what is. When you combine everything we have followed so far, the distances that stretch beyond intuition, the travel times that outlast civilizations, the biological drift of generation ships, and the fact that stars themselves refuse to stay still, a different picture of the universe begins to emerge, one that quietly reshapes the famous question often called the Fermi paradox, the simple and unsettling puzzle that asks, if the galaxy is so vast, so old, and filled with hundreds of billions of stars, many older than the sun, why have we never seen clear evidence of other civilizations? The usual answers imagine rarity, self-destruction, or deliberate silence. But there is another possibility that grows naturally out of the physics we have been examining. The idea that intelligent life may not be rare at all, and that the real barrier is not existence but contact. The structure of space-time itself may isolate civilization so effectively that even a galaxy full of intelligence remains observationally quiet. Consider what it would take for two civilizations on opposite sides of the Milky Way to interact in any meaningful way, even if both possess advanced technology and manage to transmit signals at the speed of light. Communication alone would require tens of thousands of years for a single exchange. A greeting sent from one side would reach the other long after the society that transmitted it had transformed or disappeared, and any reply would arrive equally late. Dialogue becomes impossible because conversation depends on shared time, and shared time vanishes across galactic distances. Without communication, coordination collapses. Without coordination, no shared culture or alliance can emerge. Each civilization evolves in isolation, unaware of the detailed histories unfolding elsewhere, separated not by hostility, but by the geometry of space and the limits of causality. Travel does not solve the problem. As we have seen, journeys across the galaxy require spans so long that the travelers themselves diverge from their origin and destinations shift during transit. Even if multiple civilizations attempt expansion, they would not spread as a unified wave, but as isolated pockets, each drifting through time as much as space. The result is not a connected galactic community, but a scattered archipelago of independent histories. From a distance, the galaxy could contain many intelligent species, each thriving within its own region, each lighting up its local sky with technology and culture, yet none able to maintain sustained contact with the others. The silence we observe would not indicate emptiness, but separation. This perspective also changes the meaning of observation. We might detect faint signs of distant activity, unusual radio emissions, artificial-looking spectra, or anomalies in stellar environments. But any such signal would represent a past state. By the time the light reaches us, the originating civilization may have already changed beyond recognition. We would be studying relics, not neighbors. They, in turn, would see us as we were tens of thousands of years ago. If they noticed us at all, mutual awareness becomes asynchronous, each side perceiving the other as a historical curiosity rather than a contemporary presence. The universe, in this sense, allows knowledge without proximity, awareness without encounter. The idea of a cosmic quarantine follows naturally from this arrangement. It is not imposed by design or intention, but emerges from fundamental constants. The speed of light limits interaction, vast distances dilute signals, and long travel times fracture continuity. Each civilization becomes confined to a region where communication remains practical and travel remains meaningful. Beyond that region, interaction fades into speculation. The galaxy does not forbid expansion outright, but it prevents cohesion, ensuring that any spreading intelligence fragments into isolated branches, the Milky Way, therefore, may not be a shared stage, but a mosaic of disconnected stories unfolding simultaneously, yet never intersecting. Seen this way, the night sky acquires a different tone. The stars no longer represent empty destinations waiting for exploration, nor do they necessarily conceal a universe devoid of life. They become markers of distance that preserve separation, points of light belonging to histories that may exist but remain unreachable in practice. Humanity's future, under these constraints, likely unfolds locally. Within the region, we can influence and understand. Whether others exist elsewhere becomes less important than what we do within our own sphere. Because the structure of the cosmos suggests that every civilization, including ours, develops largely alone, shaped more by its immediate environment than by any broader galactic society.